We'll do a large design problem today, a slightly larger one, and that will be directly related. If you are able to focus and pick up on today's problem, I think we would have solved pretty much 3/4 of your project, right? We would have solved 3/4 of your project, and we would also maybe, if you're able to focus, maybe guarantee you about 60 or about 50 marks in your final exam, 50 out of 100. So yeah. Okay. Alright guys, so this is the problem. So this is the problem. Looks very, very similar to your particular project problem. Your project problem is of course a bit more difficult, but if you get the hang of it, if you get the hang of it, you'll start to pick up on what we're talking about, right? Your project, I'll talk about your project problem later, but let's attempt this problem. So it says design a synchronous counter that goes through the sequence 13574206 and then repeat. So it's just going in one direction, single direction, right? Okay, so this particular problem sheet, I've loaded it online. It's just a simple one-sentence problem. It says you use using, I think the word using got messed up, using T flip-flops and using SR flip-flops, right? Using T flip-flops and SR flip-flops. Okay. All right. Now, let's make some observations over here. Firstly, is there any system input? Similar to your lab problem. Is there any system input? No, there's no input, system input X saying, okay, the direction is forward and the direction is reverse, right? In your particular project problem, there is a system input, right? Is that correct? You go forward and then the reverse. Okay, right. So that's the first observation. Let's make the second observation. The second observation is, what is the largest number? So basically, the way this thing works is, you have some circuitry. Circuitry is connected to some 7-segment display decoder, which is connected to the 7-segment display, right? So you have your flip-flop, your sequential logic circuitry, and it's saying using T flip-flops. We'll try the T flip-flops, right? Then it's showing on the first clock pulse. What does the word pulse mean? Clock pulse or clock trigger. That means the word clock trigger means it goes high and then low. So one full trigger, one complete cycle, yeah? Goes high and then low, or goes low and then high again, right? So one complete cycle. So after one cycle of the clock pulse, all the flip-flops, we don't know how many, it will decide shortly, all the flip-flops, they will show the number 1. They will show a configuration which will be the number 1. And basically in the end, your 7-segment display will show the number 1. The next clock pulse, somebody presses a clock pulse, can be a button as well, eh? Somebody presses a button and then lifts the button, like a press button, push button. Somebody presses the push button again, which is connected to clock. It shows the number 3, then 5, then 7, then 4, then 2, then 0, then 6, and after 6 returns back to 1, right? And it goes over and over, so it's going in a circle. So you call these things a ring counter. A ring counter, right? All right, let's talk about a ring counter. Okay, so let's have a look at it. Okay, this problem is on the Moodle shell. I've placed this on there, right? And if we do this problem, you are halfway, 50% way through your project, and also they'll help you in your final exam. In the final exam, you've also got a ring counter problem, right? Okay. So this is something called a ring counter. Ring counter. Now let's see the sequence over here. Let's show you why it's called a ring counter. First number was 1, right? Then 3, then 5, then 7, 4, 1, 3, 5, 7, then 4. Oh, 2 was here. Oh, 2, then 0, 6. Okay, put it at close distance. 6, right? And what direction is it going in? So after every clock pulse, it's going in this direction. Set. Everyone happy with that? That's our ring counter, right? And you can see why it's called a ring counter, right? Okay, it goes around in a complete cycle. It's a ring, right? Okay. Now, you know what the one in both directions? That's called Lord of the Rings. You know, I'm joking. Okay, all right. Okay, all right. Okay. So over here, there's no control input. All right. There's no control input. Like in your project is also a ring counter, but your sequence is different. Of course, over here we've got a sequence. We've got a sequence which is which is in a particular which has got a few set of numbers. You've got a larger sequence. I think your ones go till the number 15 or something, right? Okay, and some numbers are missing. Like over here, if you look at it, all the numbers are catered for. 1 is here, 2, 3, 4, 5, 6, 7, 0. Okay, so we're going from 0 to 7. And in your one, some numbers are missing. I think you've got a set of 10 numbers in your project. And sometimes the number is going above 9. Sometimes the number is 15. But yeah, it's in that range from 0 to 15. All right? Okay, now, this is the ring counter. Now, what is the largest number? The largest number is 7. Therefore, we can fit this in. How many flip-flops will we need to accommodate the number? How many bits do we need to accommodate the number 7, the largest number? We need 3 bits, right? If we have 3 bits, right, so 7, okay, so largest number is 7, which is 111, which is 3 bits. Therefore, 3 flip-flops. Right? Set. Everyone happy with this? Okay, so we need 3 flip-flops for this. All right. So let's now translate our particular ring counter into binary. That's the next step. Right now, we're just showing what it wanted in decimal. Right? And there's no control. Remember, there's no control. In your project, there's a control. So if x is equal to 1, it's going clockwise. And if it's x is equal to 0, it's going anti-clockwise. So you've got to accommodate that in your state table, right? State excitation table. But over here, there's no control. It's just going in one direction continually. So we're happy with that, all right? Okay, now, let's now convert our state diagram. That was a state diagram of the ring counter for our particular problem. Now, so let's do it. So that's 0, 0, 1. There'll be 0, 1, 1. Next is number 5, yeah? What's that? 0, 1, 0, 1. 1, 1, 1. Yeah, 1, 1, 1. Then the next one is 1, 0, 0. Next one, 0, 1, 0. Next one, 0, 0, 0. Next one, 1, 1, 0. Is that right? So if you look at it, okay, there we go. What have we done? We've converted our state diagram to a binary format. Now, this is something which we're used to, right? Now, this is still in diagram form, right? So basically this was 1, 3, 5, 7, 4, 2, 0, 6, 1, and it goes around, around, around. All right, okay, now, okay. Now, the next step is, as per what we did in our lectures last week, Thursday, is we convert this into a table. So all we're doing is, we're just playing around with formatting. First it was in decimal format, the state diagram. Now we are building a counter in binary, right? We've converted it to binary so we can reflect on how many flip-flops and all that. So this could be the most significant flip-flop, middle, least significant flip-flop, right? So remember, each flip-flop holds 1 bit, and we need 3 flip-flops. 3 flip-flops. So we need to have 3 flip-flops. And we've already been told in the question, hey, use a T flip-flop, right? Use a T flip-flop. Okay, so let's now put this in a table. They call this the circuit excitation table. Okay. Okay. Circuit excitation table. Here we go. So what do? We have our current state. So let's call each of these 3 flip-flops we need. We need 3 flip-flops. And so we have current. Let me zoom in. Current state. Next state. We know our next state, yeah? And this is our flip-flop inputs. Okay, current state will be, let's use the word Q2, Q1, Q0, where Q0 is the least significant, right? I'll just write it down over here. This guy here is the least significant bit. This guy here is the most significant bit, right? Everyone happy with that? Set, least significant bit, most significant bit. All right, obviously if you've got Q3, Q2, Q1, Q0, what would you say over here? You'll have Q3, Q2, star, thank you. Q1, star, Q0, star. All right, now this information is known, right? This information is known as well. Flip-flop inputs. What flip-flop do we have to use? We've been told to use the T2, different color, T flip-flop, T2, T1, T0, and also SR, right? So let's just put it in the same table, just to help us out over here. One shot. Let's do the problem one shot. So it's S2, R2, S1, R1, S0, R0. Set. Okay, and we can pull a line here, nicely over here, nicely. Okay, put those in pairs. All right. Okay, now. Okay, let's now look at our state diagram. I want you to look at your diagram. I hope it's on the same page or on the page beside it so that you can look at it. This is the main guy over here. All right, okay. So now, for starters, what we do is, what we will do is, we just populate this side of the table, eh? So we populate this side of the table with a 0, 0, 0, 0, 0, 1. There are 3 combinations, therefore, 3 flip-flops, therefore, 8 possible combinations. Hey, if there was, just to let you know, if there was a direction bit over here, let's say X input, right, to control the direction. X is 0, it goes forward, X is 1, it goes reverse. How many possible combinations would you have had? 16. There would have been another title over here called the system input. Remember that one? System input. So 16. So therefore, what can you tell me is different about our state table compared to your project state table? You have a direction bit, right? You have a direction bit. Okay? All right, so therefore that adds to your possible combinations on the left hand side. How many of you have actually seen your, read your project questionnaire, project question paper, right? And it's a small question except for because there's 100 students combination I had to give. So how many of you guys read it? How many of you have started to think about it, like draw a block diagram? Okay, this is what it should look like, and so forth. All right, okay, this problem will help you, right? This problem will help you. 0, 1, 0, 0, 1, 1. 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. All right, everyone is happy with doing the input combinations. They're fairly standard. Okay, now, as far as the next states are concerned, okay, let's now look at your, remember we first did the ring counter, we did the state diagram of the ring counter in decimal form. We did it in decimal form, just from the question. But decimal does not help us because we want to look at it in bit form, right? Because our design is in bit form. So we translate into this. So let's now have a look. So if it's 0, 0, 0, on the next count, what will it become? On the next clock trigger, it will become 1, 1, 0. So let's now do that. Let's now follow that up. Okay? 0, 0, 0 becomes 1, 1, 0. 0, 0, 1 becomes 0. I'm following you guys. I'm not looking at mine. 0, 1, 1. 0, 1, 0 becomes 0, 0, 0. Okay, 0, 1, 1 becomes 1, 0, 1. 1, 0, 0 becomes 0, 1, 0. 101 becomes 111. 110, 001, and 111, 100. All right, now, at this point in time, we now come to a situation. We have our current state, right? That's automatically populated using just all the possible combinations. We have our desired state, where we want to travel to in the next clock pulse, right? With the clock pulse, where should we be heading to? We want to find out our input into the flip-flop, which will drive us from here to here. Okay, that's basically the question. We have our current state, we have our desired state, next state, right? We want to find out what should be the input into the flip-flop, which will make it flip from, let's say, 0 to 1. So now, in order to do that, I want you to quickly, let's come here. This is important. This exam paper is very important. It was last week's paper. Yeah, right. Okay. There we go. Okay. For that particular purpose, for those of you who have been reading this, you would see that this table, that table, they're all related. And so is this state diagram. That's a state diagram. That state diagram is for this. So if you have a 0 thing, it'll stay at 1. and so forth. All right, now I want you to just quickly copy down the state table for the T flip-flop. And then after this, we copy down in your exercise book, because we'll be referring to this, all right? We'll be referring to this. All right, so it's just 4 lines, excitation table. This here is the characteristic table that's done in analysis. This is the excitation table. All right. Okay, now the other one is the SR one. Okay, copy the SR as well, because we've got 2 questions to do, and we're trying to do both questions one go. That's the SR table. Excitation table. Okay, now the reason why I made you copy it, because we don't need to flip back and forth between the 2 screens. Okay, all happy? Okay, now guys, just to let you know, in class I've taken you right in the beginning, week 8 or week 9 somewhere. I took you through all the basics of SR. I showed you, oh, this is how we build the SR latch. Then if you put a clock cycle, some NAND gates to make the clock button, this is the SR flip-flop. From the SR flip-flop, we got the truth table for the SR flip-flop. Then we got the characteristic table. Then we got the characteristic table, then we extracted the formula. Then from the formula and the characteristic table, we found the excitation table. Yeah? An excitation table, and this is the same thing. All right, now. Okay, now, and then very quickly I showed you for the D flip-flop as well, yeah? How to build the D flip-flop. The 2 flip-flops which we haven't done is JK and T, right? But the method of applying is the same. The application method in your design process is all the same. And very shortly, I will take you back after we've done the design, because I want to teach you guys design for the purpose of your project. Then I'll go back to the building blocks and show you what's inside this. So it's something similar to for example, you guys learnt about an AND gate. The AND gate is sitting on a chip, but we never taught you what is sitting inside the chip. What sort of electronics is sitting inside the chip, right? And maybe as you finish off with MOSFETs, in your E212, you will now start to learn about how to use MOSFET. Where are you in E212, by the way? OPEP. So you guys have finished MOSFETs. Okay, so when you studied MOSFETs, one of the applications of MOSFETs was for it to be used in switching, right? Switching, yeah. So MOSFETs is used to build AND gate, NAND gate, and so forth, right? NOT gate. So from there, that's how we build our AND gates and OR gates and so forth, right? Okay, and then from there we build this. So once we have done the design process, I'll take you back and I'll show you how our T flip-flop was built from scratch, and how our JK flip-flop was built from scratch. I've shown you 1, I've shown you 2. I've shown you SR and I've shown you D, right? And how we derive those tables. So right now you just use these tables. The tables will be given to you in your final exam, right? These tables over here will be given as is. In fact, it's the same particular thing. I don't even know if I've changed this 2018 to 2019 or not, but yeah, okay, so we're going to use the same one. All right, the important part is for you to know how to apply it. I will show you the derivation of the tables next week, around next week, the derivation. All right, okay, now you've copied that. Let's come back to our problem. We now want to fill up these rows here. All right. Now the way to do it is you have to match flip-flop to flip-flop, Q2 to Q2 star. All right. Now look at your T table. Let's do the T side first. All right. Q2 is 0, Q2 star is 1. So current state is 0, next state is 1. What should T2 be? There'll be a 1. All right. So let's do this. 0, 0 will give you a 0. 0, 0 will give you a 0. 0, 1 will give you a 1. 1, 0 will give you a 1. 1, 1 will give you a 0. 1, 0 will give you a 1. 1, 1 will give you a 0. Let's look at these two. 0, 1 will give you a 1. 0, 1 will give you a 1. Do you see what I'm doing now? I'm looking at the excitation table which you have just copied into your exercise book, right? But look at where my two fingers are. 0, 1 gives you a 1. Your current state and your next state, right? You have to fuse it together. Q1 to Q1 star. 1, 0 gives you a 1. 1, 0 gives you a 1. 1, 0, 1 gives you a 1. 0, 1 gives you a 1. 1, 0 gives you a 1. 1, 0 gives you a 1. Let's go to the last one. 0, 0 gives you a 0. 1, 1 gives you a 1. Oh, sorry. Yeah, 0. 0, 0 gives you a 0. 1, 1 gives you a 0. 0, 0 gives you a 0. 1, 1 gives you a 0. 0, 1 gives you a 1. 0, 1 gives you a 1. We filled all. Let's call it out now. So flip-flop 2. So 0, 1, the first line will give you S2R2. The guys in the front? 1, 0? Yeah, is that right? Okay, second line? 0x. 0x again. 1, 0. 0, 1. X0. 0, 1. Right? Okay, let's guys at the, who was doing the one on the right hand side? The S1R1. Okay, right? So the first line, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1. All right. All right, the guys at the back now. 0x, x0, 0x, x0, 0x, x0, 1, 0. All right. Okay, so that's our circuit excitation table. Now it doesn't stop there. Let's do the T flip-flop design. Hey, and in your question, in your project, so basically that's what the reason why I chose this particular question is it's a small question which we can do in class, but it doesn't do your entire project for you, all right? There's some parts which are still you've got to handle. Like for example, the first difference was you have the first difference was you have over here, right on the left hand side, input X, which controls your forward and reverse direction, right? So obviously if you have 0 over here, it'll be going in the forward direction. If you have 1, you have to look at from your particular state diagram what the new values for your next are, right? Okay, now the other thing is sometimes in your project there's no system output. Sometimes there's a system output to show that maybe a light bulb showing that you have reached above some number, right? Let's say if it's a light bulb to show whether the number is above 10 or above the number 9. The light bulb goes on and light bulb stays off for below 9. Or odd numbers it stays on, even numbers it's off. I should have given that in the project. Okay, system output, right? Okay, maybe we can modify the project. All right, okay, all right. Okay, now the next one is all right, we've got T flip-flop. Over here we're using one flip-flop. So the first part of our design is we're using one flip-flop. Now in your project, I think you've got problem 1 and problem 2. Yeah? Problem 1 and problem 2. Problem 2 is just like this. Problem 2 is just like this. Of course you've got the input X, but you're using only one flip-flop. Yeah? Only one flip-flop. It's either the SR or the JK, if I remember correctly. Yeah? Problem 2. But with problem 1, you've got to use a mix of flip-flops. You've got to use a mix of flip-flops. So let's say if you end up with 3 flip-flops, so you've got to have one, let's say if they asked you to use JK and D, right? JK and D combination. So you'll have JK. Out of the 3, 2 will be, you've got to do half and half, right? But obviously you can't divide 3 by 2. You can't divide 3 by 2. So 2 of them you can use, let's say, JK or D, and the 1 you can use JK. So either it will be JK, JK, D, or D, D, JK, or JK, D, JK, all right? Or D, JK, JK, all right? Okay? Or D, JK, D. You get the picture. So it's got to be a mix. All right? Okay, that's the difference about problem number 1. In problem number 1, this particular column will not be the same flip-flop. It's a mix of those 2 flip-flops. So let me just show you. Let's just go quickly to the diagram. So this is important class for those of you who want to get ahead with time with there we go. Project. That's your sequence, goes all the way and then repeat in the forward direction, and then of course there's a reverse direction. It says a combination of 2 different flip-flops when assigned for Q1, you must use both. You have to use a mix of both flip-flops approximating to a 50-50 ratio. This means that half of the flip-flops in your design should use the first flip-flop while the remainder should use the second flip-flop. Right, you're free to use. So let's say this first guy over here. Is he here? Okay. All right. D and JK, right? So, okay, even the second guy, T and SR, right? Okay, so question 2 is just like this, just like what we are doing right now. Question 1, you've got to use a mix, right? You've got to use a mix, which means it won't be all T, it will be a mix. And then obviously that column, you've got to go to that respective flip-flop. For that column, you've got to go to the right flip-flop excitation table, right? For the next column, if let's say if this was D, JK, JK, so the first column we use D, right? And then the second column we've got to go use the excitation table for the JK flip-flop, right? So we've got to do half and half. All right. Okay, now let's come to this thing here. Now that we've got T2, we've got to find a formula for T2. And the way to do it is we draw a Karnaugh map. Right, a K-map, right, and these are our inputs. You've got Q2, Q1, Q0. It's up to you how you draw your Karnaugh map. You can even make a vertical Karnaugh map, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. And similarly, you've got T1, all right, and you've got another third Karnaugh map. Remember, how do we know our Karnaugh maps? From here, eh? From here, our design. This was using, the first problem said you design using T flip-flops, right? And our third Karnaugh map was T0. All right, guys. There we go. Now we've got the formulas. Now in your case, how do we decide this? These are the inputs into our flip-flops. So for example, if the question said, like part 2 of the question said, design using SR flip-flop. So how many Karnaugh maps would we been doing for this particular problem? For part 2, this we are solving the part 1 problem. 6, 1 Karnaugh map for S, 1 Karnaugh map for R, 1 Karnaugh map for S2, R2, then S1, R1, S0, R0. So 6 Karnaugh maps altogether. You see there's a lot of Karnaugh maps. Now, let's do the T1, because in the T flip-flop, how many inputs? Only one input into the T flip-flop. So therefore, we only have to do one each for each flip-flop. All right, now let's fill up these Karnaugh maps. Let's fill up these Karnaugh maps. All right, okay. So very easy. Same procedure like what you did in the first 5 weeks. 0, 0, 0, and this is 1. Yeah, T2 is 1. So 0, 0, 0, T2 is 1. Right, let's move to the next line. Right, 0, 0, 1. 0, 0, 1, and T2 is 0. 0, 0, 1, and T2 is 0. 0, 0, 0, 1, 0. That's a 0. So, hey, if you want to use the window method, you know, we already know the window numbers, and you can quickly populate these, eh? All right, so we can quickly do these just using. Do you remember that technique? Yeah, just by following the window numbers, right? The cell numbers. Let's do it for T1. Hey, did T1 have all ones? All right, that's good. Makes it easy. All right, what about T0? 0, 0, 0, 0, 0, 0, 1, 1. Let me know if I've made a mistake over here, all right? After this, we'll do one more step. Everyone happy with that, guys? Right, don't copy me. You can follow from the truth table, all right? All right, okay. Now, let's do the groupings for this guy. So obviously these two can hook up together. This guy here, no partner. There's no way to, there's no way to move for him. This one here can go this way and that way. Therefore, can you tell me what is T2 equal to? T2 will equal to, there will be Q naught bar and Q2, yeah, this guy here. Is that equal to Q2? Q2, or what would this do? This one, there will be Q naught bar again. Q naught bar, and what's these two over here, guys? These two. Q1 bar, and what's this last guy sitting alone? That's Q naught, Q1, Q2 bar, right? Right, everyone saw what I did there? Okay, now this guy here, let's look at it. That's a unique situation. That's one big group of 8. What do you think is the answer? Yeah, the answer is just 1. T1 is equal to 1. All right, because it's the whole Karnaugh map is just ones. It's fixed to 1. All right, now this one here, what will that equal to? T0 would equal to Q1, Q2, right? Is that correct? Right. Now let's look at the circuit. The circuit is also important, and this is the part which you will be doing in your particular project, like in your software, in your Logisim or Circuit Maker or whatever software you wish to use. All right, I'm just going to put that on the side. All right, we've got the formulas. So there's 3 flip-flops. 1, 2, 3. That's your clock line. That's our clock line. We don't worry about our clock line because we just know that it's just doing the triggering, all right, but doesn't contain real information, just triggers it to the next state. Right, that's the importance of the clock line, triggers it to the next state, makes it move, all right? Okay, you've got your Q, let's call this 2, right? 2, 1, 0, Q2, Q2 bar, Q1, Q1 bar, ignore that bar there. Q0, Q0 bar. Set? Everyone happy? Right? And what do we have over here, guys? There's one input, right? T. T2, T1, T0. All right, now let's hook it up. Okay, T1 is probably the easiest. T1 was the easiest. Why? All we got to do is supply a logic 1. Yeah, that was the easiest one to do. No hassle about that. Now let's look at T0. Let's do the easy ones first. T0 has got a simple AND gate of Q1 and Q2, right? Yeah? So that's an AND gate. AND gate. Right? And we have Q1 and Q2. Q1. Right, so that's Q1 over there. And Q2. So we've sorted out 2 of them. Right, that's Q1, Q2. That's our 1 over here. Anything else? Did you guys see I did a jump over here? Okay, now let's do the T2 one. T2. That's an OR gate. Firstly, that's an OR gate. Right? Plugged into that. And into the OR gate, you have Q0 bar. You have 3 NOT gates. 3 AND gates, sorry. Okay. Got 3 AND gates. 1 AND gate here. One AND gate here. 1 AND gate there. All right. Okay, now let's populate that AND gate. Q0 bar and Q2. Q0 bar is this guy, right at the bottom. Q0 bar and Q2. How will we do that guy? Okay, jump the clock line. There, that's Q0 bar. Right, this guy here also goes into the second guy as well. Yeah, can you see Q0 bar is used twice? It's used twice. Q0 bar. Right. Okay. And it says NQ2. Yeah, NQ2. That's Q2, right? That's Q2 over here. Go there. There. If I can squeeze this guy here in. There. That's Q2. Set? Everyone happy? That's Q0 bar and Q2. So my output over here is Q0 bar and Q2. Can you see that guy? Alright, that's from here. Q0 bar and Q2. Now Q0 bar and Q1 bar. How will we do that? Right. Q0 bar and Q1 bar. Okay, go down this way. That's Q1 bar. Go down this way. Come up here.